Hi everyone, welcome to this webinar on Yocto versus Ubuntu Core for your embedded Linux project. I'm Edoardo, a product manager at Canonical, and as a disclaimer, there is no endorsement or sponsorship of any kind by Yocto or by Buildroot or by Open Embedded for this webinar. I figure we can just get started, and if somebody joins later, hopefully they'll be able to follow along regardless of the time at which they join. If you have questions, there should be a section that you can access on BrightTalk where you can ask, you can provide feedback and you can ask all your questions and add any comments, and then I'll try to answer as many as possible at the end of the presentation. So please keep adding those questions, and then I will answer them at the end. In terms of what I would like to cover today, um, if I want to divide the presentation in four main areas: Yocto, Ubuntu Core, buy versus build, and Yocto versus Ubuntu Core. So let me explain what I mean by that. When it comes to Yocto, I want to first of all introduce this extremely popular open source collaboration project that helps developers to create custom Linux based systems. So to understand how Yocto enables developers to do that, I will very briefly go through its history. I will introduce the end product that you can obtain via Yocto, and also go into some of the specifics of how Yocto enables developers to create those distribution. So we will look at the recipes, at layers, and at the board support packages in Yocto. And we will understand how Yocto specifies what software to build and how to build it in the recipes. Also, how you can support new boards and new architectures via the layers, and how you can define new application stacks. So we will have, I believe, a really good understanding of also the inner workings of Yocto, as well as the pros and cons of going through that process to create those embedded Linux distributions. Then we will move on to present Ubuntu Core, which is essentially Ubuntu for IoT and embedded environments, and its inner constituents, so the snaps, these containerized software packages, and also how the snap store can deliver updates and distribute and deploy applications to the end devices. Then we will, before going deeply into a comparison between Yocto and Ubuntu Core, I want to set the stage and provide some context for that comparison by looking at the commercial versus roll your own debate around embedded Linux. Should you make it yourself? Should you buy it? And what are the main considerations going into that decision? With that in mind, then we can take a look at Yocto versus Ubuntu Core. This will be a direct one-on-one comparison between the two platforms, and we will address many several points, not just the three ones that I reported here. We will have a very broad understanding of the advantages and disadvantages of using one versus the other. What are the best use cases as to when one should employ one of those two platforms. So try to stick towards the end for this final comparison. All right, let's get started. So uh, as I said, Yocto, it is a very actively maintained project, and the end goal of Yocto is to enable developers to build a complete, a customized embedded Linux system. So Yocto is a family of open source project. It is called the Yocto Project, and it allows developers to build embedded Linux distros from scratch. At the core of the Yocto project is the Open Embedded Build System and the Poker Reference Distribution. So to understand how those two pieces came about to form what is today Yocto, we need to look at very briefly at its history. So in the early 2000s, there was this Open Zaurus project, which was an open source project that was trying to improve, to make more frictionless the writing the code of the first personal digital assistants that were based on Linux. A few years after, around 2003, the Open Embedded project came around, And what it tried to do was to combine the efforts of this open source project, but also contributions from other embedded Linux projects that share similar goals, like OpenSymPad projects. So essentially, we had a group of distributed developers that were all contributing to the same vision to create the next generation of PDA, of personal digital assistants, to create the Linux OSs for those devices. So Open Embedded uh, combined those several projects, and it started to maintain the build system and the metadata that described how to build the software packages and how to assemble those images as a common code base. Later, towards 2005, the project team split in two, so the bit-bake build system and the open embedded metadata. And I think it's fair to say that Open Embedded significantly simplified building those Linux OS stacks for devices, for embedded devices. But there was still a challenge because of the steep learning curve that was needed to be able to modify, to adapt the system, to create, to port it to different to new hardware, to create different distributions. So there was a software startup called OpenHand that developed Poki Linux. And Poki Linux was a distribution that provided a more uh, intuitive way to configure those images for target devices. So essentially, it was trying to solve the pain points that Open Embedded highlighted from combining OpenZarus and OpenSymPad projects. And Intel came along in 2008. It acquired Poki Linux with the goal to develop this universal Linux distribution for embedded devices. Finally, towards 2010, Intel approached the Linux Foundation with the idea to with the idea to create a collaborative project to build Poki Linux to support more architectures, more hardware, and make it the default solution. And in 2010, the Linux Foundation announced the launch of the Yocto project. So Poki Linux was originally developed by OpenHand, and it evolved into the Yocto project together with the efforts coming from Open Embedded, which was combining previous open source projects dating back from the early 2000s. Nowadays, Open Embedded and the Yocto projects, they are two separate entities, but they collaborate together. So they have the same vision. They are aligned into making into enabling developers to build those embedded Linux distros from scratch. But they are supported by corporations and they are independent between one another. So Yocto is extremely popular professionally, and I would argue it is among the preferred platforms in the industry. Um, some commercial embedded Linux vendors like MontaVista or Mentor Graphics, they all use it because of its industry-wide support, and also several silicon vendors like when it comes from ARM to MIPS, PowerPC, and x86 architectures, there is an industry-wide support from all sort of chip vendors of different architectures. This is a key aspect of Yocto, and also Yocto is completely customizable for your board. It is versatile. It allows developers to build these custom Linux distributions for a wide range of embedded devices, of embedded systems. At its basic level, Yocto gives you a root file system image for the device with a kernel, with a bootloader, and with a compatible toolchain. Um, I think the best way to get a feeling directly for what goes into Yocto is to just get our hands dirty. So I want to bring up my terminal. Hopefully you can all see it. And Yocto includes several blueprints for typical Linux OS stacks. So I want to show you what I mean by those blueprints, by those reference images. So let's just discuss a couple of those. For instance, this one. This is the most basic image, which allows a device to boot with a kernel, a Linux kernel, and it includes an initial root file system that is based in RAM. Similarly, we also have other images here. It adds a typical CLI tools like Bash and many more to the root file system. And all of these example images, they offer these root file system configurations from which then developers can expand and create their own custom distros by extending them. So they are blueprints that for typical Linux stacks from which developers can then go and create their own end solution. Um, I think two aspects clarify the approach that Yocto takes to enable this flexibility. And one is defining builds in recipes. And those recipes specify what software to build and also how to build it. Essentially, a recipe is just a metadata file that contains all the necessary information for the build engine on how to build that particular software package. So the build in Yocto happens via bitbake, and it takes config files and recipes as inputs. And again, let's just take a look. So recipes follow a standard layout that is broken into separate sections that group the metadata into a logical way. Um, Let me open this one. So I will go through more or less most of what goes into the standard layout of a recipe in Yocto by taking a look at an example one. So first of all, recipes use the BB from bitbake file extension, and the bitbake is how the build happens in Yocto, right? And this recipe, we can see from the top, the very first attributes, they are the descriptive metadata, which provides information about the recipe and the software package it wants to build. And for instance, here we can see where the software package is hosted. Uh, the following attributes, here we see just one, that they depend on the package manager metadata section of the recipe. So all the package management tools of your Linux distro, they will use the section category to organize the packages. There may be other entities, other attributes that are not shown in this specific recipe, but they all form the package manager metadata section of this recipe. Then we have the licensing metadata, and all the way from where I'm highlighting all the way to, let me take a look, all the way to here. This is all the build metadata. What do I mean by this? So we have the dependencies here with the package name SPN as well as the package version with PV. And the recipes describe the dependencies during build in this part of the section. This instead is where Yocto will find the source code, will find the patches, and where other files will be downloaded from. Um, Similarly, we have this information here, which is where developers can modify it, and it allows you to enable and to disable features of a software package at build time. So you can just specify that information under these attributes. Now, if we scroll down, this remaining part of the recipe file, this is the packaging metadata information that is required after the build. This specifies how to create the package software bundle. And we also have dependencies. If I scroll a bit down here, these are the dependencies that occur during runtime on other software packages. So we saw the build dependencies, and now we have the runtime dependencies with, again, the PN stands for package name. So from just taking a very brief look at the layout of a recipe, I think you can see how overall a recipe in a Yocto project describes where to obtain the source code, how to build the binaries, what are the runtime dependencies, what are the build time dependencies, and also how to install the build resource on a target system. So Yocto is very flexible and customizable, but as we saw from this layout, it does expose a lot of a lot of complexity or information to the end user. Now, the other way that I want to mention that in which Yocto provides this high degree of configurability to the end users is by supporting layers. And layers, they are essentially recipe collections that are written and the community maintains them. So a layer is just a collection of metadata. It is organized into a specific file and directory structure. Um, and for instance, here we will take a look at the Raspberry Pi layer. And layers are what allow developers to support new boards, to define new application stacks or new architectures, because you can edit the existing layers to add support for new hardware without having to completely rewrite the original layer. So this is one of the key advantages of Yocto, that it is relatively simple to reuse existing layers, existing definitions. And there are many layers because there is an active community contributing to those. So Yocto defines a build with a collection of layers, and they are what enables a strict separation between the core of the build, the board support package, and the custom modifications to support new use cases. And this separation is it's a smart feature of Yocto because it allows a configuration to properly scale. The Yocto project BSPs, the board support packages, they are also provided as layers. And imagine if you are a silicon vendor, for instance, and you want the end developers you want them to build and to run the embedded OS on your custom hardware. It would be in your best interest to provide developers with those board support packages. And in Yocto, the BSP layers are tailored to a specific embedded board. So the BSPs of the Yocto project are metadata layers that include some specific configurations, some additions to the underlying layers to support the target hardware. So I want to show you the generic BSP layer layout of a Yocto project inside the Yocto project. So here we're taking a look at the one for Raspberry Pi, and we can see the README file that is in the top level directory of the BSP, and it describes, of course, the board support package and and the target hardware, and it also lists the dependencies for this specific layer. Now, if we go inside this section, the layer configuration file with its dependencies, this is where um, core is the open embedded core metadata layer, and so under layer.conf we can see the the config information of this specific Raspberry Pi layer where we are in. If we switch towards here, so the machine definition is what specifies how a BSP layer will differ from a regular layer. And it is in the form of a configuration file with the name of the machine.conf, and they are located inside the machine subdirectory of the BSP layer. And the machine configuration, it describes the architecture and the hardware features, as maybe you can understand from taking a look at it. And I think one of the great aspects of Yocto is that several silicon vendors have BSPs based on Yocto. So we can also see how the recipe subdirectory. Let's see. This information here, they are specifics to the BSP and to the supported hardware. For instance, we're going to have information on the kernel, like specific configuration files, but also configuration recipes for display support and tailored graphic requirements. So a specific version of a Yocto project BSP will be tied to the particular versions of the underlying layers that it depends on. Because as we saw, Yocto projects are provided as Yocto project BSPs, they are provided as layers. But like what this means is that if the underlying layer were to change, for instance, if the meta layer was to drop support for a particular kernel version, then also the derived BSP must be adapted. So the maintenance of a Yocto project BSP is a relatively painful project because of all the packages that the BSP adds and all the underlying layers ones that it is going to modify. Um, Also, if manufacturers they build BSPs constantly, like they are constantly changing with new releases. So if you need to update or to upgrade a BSP, there is no immediate way of doing so. Like everything fails and you need to start from scratch when there is a new release, when there is a new BSP. So the more we'll go into this description, I want to cover later around updates and security and how Yocto handles those in the comparison with Ubuntu Core. But overall, with the Yocto project, you will create a distribution to your own specification. It is fully configurable. You can build it from scratch from upstream source code, and it gives you this extreme flexibility because, as we saw from the recipes, from the blueprint images, you can control essentially every stage of compiling and building the target. Also, Yocto keeps the configuration information in multiple parts, right? We saw how the distribution configuration of the recipe, it dictates the packages, the tool chains, and the libraries. Then there's the machine configuration, the machine subdirectory, which describes the architecture and the other features, as well as the image recipe, which lists which packages should be pre-installed. Um, so all these different bits and pieces, essentially it means that you may need to gather a lot of layers together before you can begin a build. And but also it also means that it is easy or relatively easy to build variations because it is not too much work to reuse existing recipes and layers. There are just some additional modifications that you may require to do on top of the underlying layers, whether you want to use existing BSPs or the core layers, the blueprints that I showed you. So building for the variants of the same board can require in principle just a small tweak. However, a downside here that I do want to mention is that there tends to be some legacy. So this holds for layers in general. There are many layers and packages, which is great, but some of them are you can't rely on them for your production use cases because they may contain a lot of legacy code. So it is up to the end developer to investigate the different layers and to understand if they are maintained or not, or if they contradict one another. So overall, because of its great flexibility, Yocto also exposes lots of complexity to the end user. So there is a challenging learning curve. BitBake, it is a very big Python program, and the build system and recipes, they are written in a combination of language that is specific to BitBake, some shell scripts, some Python. So overall, there is a learning curve for custom boards, and you really must understand how BitBake operates. You must become very familiar with layers, with recipes, before you can effectively and productively make an image out of them. So to make a proper image, there is some work required, and this is one of the prices that I think developers have to pay for the extreme flexibility that the Yocto project offers. The fact that you are completely in control. So to start, this is I think a good overview of Yocto, and now I want to switch to Ubuntu Core and then circle back to the differences between the two. And Ubuntu Core, the whole idea started by trying to answer, I think, a few questions. So how do you build an embedded device at a price that is affordable for the end user? But also, how do you ensure security? And given the learnings from, for instance, the Yocto project, how do you get to market fast? How do you focus just on development, on your value-added software? How do you update the software? How do you manage your fleet of devices in the field over several years? So there were a series of questions, of considerations, of pain points in the industry that uh, Ubuntu Core addressed through its solution. So Ubuntu Core is Ubuntu for IoT and embedded environments. It is a flavor of Ubuntu with a very minimal footprint, and it is an app-centric embedded operating system based on Ubuntu. So essentially, we try to make embedded Linux easy on Ubuntu because we, like Canonical, the commercial entity behind Ubuntu, we handle the board, and the users they just focus on their applications. So there are no bad BSPs, there are no maintenance nightmares, there are no integration delays that may result from the usage of Yocto. You just develop on Ubuntu. So Ubuntu Core is Ubuntu optimized for mission critical devices and IoT. This is because it is hardened for security, because it has a minimal footprint, and because it is cryptographically locked down. So some of its key features are security, are robustness, but also being very simple to install, to maintain, and easy to upgrade. Ubuntu Core, it is an operating system built from snaps. So all components are containerized in snaps, and Ubuntu Core runs only strictly confined snaps. So what are snaps? They are containerized software packages that use standard Linux security capabilities like AppArmor, cgroups, seccomp to confine the applications. And each snap has a fake view of the world in the sense that they may not even be aware that there's a network or that there is a webcam. With snaps, you have a strict you have a fine-grained control over the permissions and the interfaces for each snap. Um, and we notice that of users and customers, like they want to develop and manage their applications using containers, and this of course can be achieved with various container runtimes, but we think that the Snap ecosystem it provides a containerization system that is focused on security, and it offers strict privileges and strict separation between the different containers. And essentially, snaps give users the kind of control that other packaging systems do not. Also, they work across a range of Linux distributions, um, which means that having one package that can be installed on 50 different Linux distros is very compelling for the developers. This saves a great amount of time to have just one package, because you don't need to rebuild, you don't need to repackage your application for every distro or for every release of the distro. And snaps are an integral part of Ubuntu Core, because in Ubuntu Core, all the components are constructed using snaps. Snaps which are updated via the Snap Store. And here we were again starting from a question: how do we focus on development for the end users? How do we make sure that they reach the most people? How do we ensure global collaboration? And in general, managing software and updates across a huge number of devices across a fleet, it is not easy to do, especially if a subset of the hardware, if they require different applications to run on them or different releases of the same application. So with the Snap Store, the delivery of automatic updates and the handling of the software across different devices, across machines, is one of its key features. It is a universal app store for any Linux distro to distribute and deploy the applications, whether they are on the device but also cloud or desktop. Um, and I think what we try to do here is to lower the barrier for software vendors who want to target Linux by providing a single platform. And the Snap ecosystem is attractive to big publishers who are constrained with their time and when it comes to supporting Linux. And to summarize, essentially, Ubuntu Core is Ubuntu with a minimal footprint. It is a modular and simple architecture provided by the Snap ecosystem. And the combination of the secure underlying OS, the combination of the Snap packages and the Snap Store, it gives developers a platform for secure open source development, for for software deployment and global collaboration. And security is a big part of the story of Ubuntu Core. So we saw that we automatically confine applications, and Ubuntu Core integrates strict AppArmor and SecComp rules for all snaps. But we also redesigned the entire system all the way from the first boot to create a very secure embedded Linux stack, so that as a manufacturer you can ship your embedded devices in a way that is cost effective, because you don't have to implement complex security features yourself, from full disk encryption to a root file system that is read only. So Canonical, the entity behind Ubuntu Core, takes care of that. And the updates are delivered by Ubuntu Core, by the store of Ubuntu Core. So there is an ultra reliable software distribution machinery that has been extensively tested in production. And here we have a managed store that gives you um, access control that is based on your role. It gives you application versioning, over-the-air updates, and control software rollouts, but also much more. Like, as a developer, you can push updates to your apps at your own cadence, and not to wait for the maintainers of the distribution to catch up on all the dependencies. And you can also host multiple versions of the app on the store, of the multiple versions of the Snap in different channels, in different risk levels, and then the end users can pick the one they prefer. So overall, Ubuntu Core is a platform. It's a platform for technology that can be used across all of IoT, from cloud to drones to cars, from fridges and robots, you can name it. Um, and in order to be part of the different things in the IoT world, in the landscape, I think you need a base that can work across all of them, that is scalable. And you need devices to be compatible, you need them to be connected, and also there must be a level of consistency across all the different IoT sectors that you may be in or you may want to move in. And this is something that Ubuntu Core focuses on, to fulfill the gaps of this hugely fragmented but rich market. And I think not no other alternatives in the market has a similar approach to development. um, let's now compare the two alternatives that I presented so far, and to provide some context and to set the stage for the one-on-one comparison between Yocto and Ubuntu Core. I want to first briefly introduce the commercial versus roll your own debate that will inform the rest of the conversation. Um, so again, the premise here is that Yocto Project, it is an open source collaboration project that enables you to create these Linux-based systems. So it is easy to build them from scratch. This is one approach you can have to embedded Linux development. The other is to buy the support for the commercial embedded Linux distro like Ubuntu Core, so that it is supported over several years rather than building your own. I think two considerations are worth highlighting here. One that is sometimes overlooked when choosing the OS is exactly this availability of commercial support. So there are some challenges that I think community maintained projects like Yocto don't address, and that will surface only after the device is shipped in production. And in general, the vendors of embedded Linux, they try to fill this gap by providing support and expertise that is enterprise grade. And this is what enables you to also ship faster to reduce your time to market. Um, and also some of the recent vulnerabilities in open source development, I think they force customers, users, they force them to think about the space, to think about open source and community maintained projects in a more sophisticated way, shall we say, rather than with blind reliance. Like developers, of course, should constantly be scanning for vulnerabilities, but as an enterprise, as an organization, you can't be dependent on the individuals. There must be a practice in place or a constant stream of reliable security updates rather than having individual contributors look at every line of code. So, if a project is open source and it is maintained by the community, it does not come with a guarantee that you are safe, and it may make sense to have a commercial partner and having a service level agreement. This is, of course, a consideration that you must make when choosing your embedded Linux OS. There is no vendor to blame in a community-driven open source project, which means that security is sometimes only handled, it only surfaces after the fact. This is different from a vendor driven project because there is an enterprise back in the development that ensures the reputation for reliability and trust is maintained. Behind security, support, etc., I think a vendor led project, they provide a more tactical approach to development. And what do I mean here? So this is something that I see the importance this plays in the eyes of the customer. I'm referring to the stable reliance on a product roadmap that is long term, because there are paid engineers. There's a team there's a professional approach in handling the performance issues, in fixing bugs, and also in evolving the software in a way that is scalable, coherent, and sustainable long term. And also that it takes into account the priorities of several stakeholders, essentially following a product centric view when prioritizing features and development. And on the other hand, the contributions of a community led project, for instance, imagine all the layers that are maintained by the community in Yocto. It may be the case that the individual contributors may not be interested in the bigger picture, in the overall architecture. And this could result in legacy code, in branches that are not maintained, in vulnerabilities, in poor testing, in technical depth. Essentially, there may be a lack of long-term thinking when it comes to the product roadmap, which as a consequence will tend to be more flexible, it will tend to be more open, but at the same time not very stable or reliable. So now that we set the stage for commercial versus roll your own, buy versus build in the embedded Linux world, I do want to go in depth into Yocto versus Ubuntu Core, into the final comparison. And we will take a look at different items and mention a few considerations for both Yocto and for both Ubuntu Core of how they handle the specific items I'm talking about. So on the left of the screen, we will have Ubuntu Core, Yocto related considerations. On the right, we will have Ubuntu Core, and I'll try my best to be objective and justify what I'm saying here. So time to market, of course, in the fast-paced world of the Internet of Things, being able to reduce this time to market is a priority. And here I'm saying that with Yocto, it is relatively slow because of the complexity and the steep learning curve that it takes. Because you need to understand layers and recipes and BSPs and bit-baked language that I showed you before, this will slow down the time to market. With Ubuntu Core, it is accelerated because there is support, there is an ecosystem around it. You just focus on your applications, and Canonical will handle the rest. The company behind Ubuntu Core, Canonical, will offer enablement, customization, and development to get your first device to market fast. And essentially, there is an enterprise support to from all the way from hardware selection to delivering the infrastructure needed to develop and the software for your fleet of devices with consulting services. The idea is to have an entire ecosystem to minimize risk and to fill any gaps that the team may have in skills. So accelerating the time to market. When it comes to maintenance of the kernel, with Yocto it is manual. You do need, and it may be perfectly fine if you have substantial expertise in-house. If you have skilled kernel engineers in your company, the maintenance effort is something that you have to do on your own. On the opposite, with Ubuntu Core, the OS is supported by Canonical. It is Ubuntu. It is the official kernel supported. It will continue to receive security updates and critical software packages. Um, also, I think the reliability of a kernel is achieved through, besides of course the very careful design process and an engineering team that is very very skilled, the volume of use in production is important here. Um, so when it comes to Ubuntu Core and Ubuntu, the volume and diversity of implementations, the more organizations that rely on a piece of software, in this case the Ubuntu Linux kernel, the more it is tested, it is refined and improved. So because the vast majority of production workloads run Ubuntu, this means that Ubuntu Linux kernel is among the most production tested kernels in the world of Linux today, and it is actively maintained by an enterprise, by Canonical. Um, on security, here I mean tracking and fixing and also the timely delivery of security patches. With Yocto, you need to ship your own security patches to the images. You are on your own. Um, Also, implementing security with with tools that are provided by manufacturers is not easy. Why? Because they take the open source software, they add some drivers to it, and they give it to the customer, right? Their goal is to sell the hardware, is not to deliver good software. So you are on your own when it comes to implementing security features. With Ubuntu Core, I mean, we try to make a step forward in providing a secure world to the entire Linux ecosystem, whether it is the Snap world, whether it is the security control, the hardening, the containerization, sandboxes in the platform. Um, there are lots of considerations that came into making Ubuntu Core, not just the Snap applications, but also the delivery times for CVE fixes, the known vulnerabilities. Essentially, it is one of the best in-class security approach to the world of embedded Linux development. OTA stands for over-the-air updates, so delivering reliable software updates to devices that may not be easy to access, that may be remote, and you may need, as a developer, as an enterprise, you may need to deliver um, some updates that are administered remotely, and the traditional mechanism, they don't always work, and they can cause the IoT devices to be unstable, and then fixing them would require an intervention that is manual, that is costly, and you will need to send your engineers on site to fix the device or to recall it from the field. And Yocto has no built-in system for over-the-air updates. Um, you need to build the device agents and the delivery network from scratch with manual scripts or with a third-party solution. So like Mender or Racing.io, there are some existing open source solutions for software updates that support the Yocto project. And for instance, Mender is an excellent choice for AB updates. With Ubuntu Core, this is supported out of the box, and they are over the air, they are Delta updates, which means that if you make a small change in a large component, Snaps will calculate the differing binary delta, and it will minimize the traffic and time required to distribute the difference to the device. So the content shipped inside the snap, inside the containerized application, will be compressed and will remain compressed and read-only throughout the entire lifetime of the snap. And in Ubuntu Core, the kernel and the OS itself, they are handled as snaps. So with all the benefits that apply to the applications, they will also apply to the kernel and the operating system. Uh, Rollback of the updates, as far as I'm aware, it is not possible with Yocto, or it is a manual approach. With Ubuntu Core, we enable automated and transactional updates that are either 100% successful or they are not installed. So um, we will keep the original version of the data of the code, so you can move the applications backward and forward in their version history. So there is an automatic recovery mechanism in place, and if there's an error, if there's a failure of the application, Ubuntu Core will stop and it will go back to the previous working version of the snap of the application. Another consideration when considering the embedded Linux OS for your device is the app ecosystem. Yocto multi-app are supported, but they are not confined. There are no app boundaries, and I would argue the application concept in Yocto is not well thought out. It is a generic RPM, and also there is no app store or path towards monetization as the device manufacturer, which may be one of your strategies, right? With Ubuntu Core, the apps are decoupled from the OS. Ubuntu is just the enabling platform, and um, we handle the infrastructure, and you just need to run the app store for your devices. And the intelligence of the device ultimately is a function of software, right? And the focus for us with Ubuntu Core is to make every device effectively app enabled. And we give manufacturers the ability to commercialize the apps through their own store. Another consideration is the developer reach, and of course investing in open source technology. It creates tremendous value for the community and for everyone involved. Yocto, it is extremely popular professionally. It is among the preferred platforms in the industries, and it is very well known to embedded developers familiar with cross compilation. Um, However, because there are no two Yocto images that are similar, developers need to target the individual devices. It doesn't scale easily in terms of developer reach. Ubuntu Core is of course tied to the App Store, where there are thousands of apps that work across the different Linux distributions. So the investment in collaboration is very clear here, and developers can write once and reach millions of devices. And Ubuntu, of course, in terms of branding, is one of the most widely used Linux distros today. Another aspect is commercially supported Kubernetes, and Kubernetes it has established itself as the modern platform to build and to run software, right, on cloud and on prem. And now we are seeing the industry shifting the attention towards the edge part of the compute spectrum. With Yocto, there is no Kubernetes integration. With Ubuntu Core, you can run them. It is a conformant Kubernetes solution into IoT. There is a minimal resource consumption. There are again automatic over-the-air updates. Essentially, we reduce the cost, the operational cost, and provide a platform for cloud-native applications. There are several other aspects worth considering when comparing Yocto and Ubuntu Core. From the opportunity cost, which means allocating resources to embedded Linux versus core activities of your business, developing the application. And buying from a vendor would free those resources that you can then allocate to the core business activities of your organization. Other aspects consider the bring up of the board, so whether it is supplied as part of the board BSP, or if it is enabled by the vendor for a fee. So there are other aspects specific to your use case that should go into the debate on Yocto versus Ubuntu Core, on the buy versus build, commercial versus roll your own. If I were to try and summarize one message that I would like you to get today is that Yocto, it has very low upfront cost because it is free and open source and available, but it has some hidden, some backloaded costs. So the lower the barrier for rolling a custom embedded Linux distro, but the cost may tend to grow over time. Because you need a dedicated team of experts looking after your Yocto distribution. And if you do, that's great. If you have a team of kernel engineers that are familiar with Yocto, I mean, that's a win solution if you did your cost calculation. It can be difficult to maintain, like keeping the kernel up to date is not easy. You need an expert team to do that, and also providing updates and security. So overall, Yocto, I think it is great if you have a dedicated team working full time on Yocto. It is also great for quick solution, for proof of concepts. And on the other end, I think Ubuntu Core, when it comes to the enablement, there are upfront fees that vendors may ask for, but these fees, they will cover a broad range of activities, from compliance, documentation, customization of user space, but they also cover the ongoing commitment from security and bug fixes. And the reference images of Ubuntu Core are of course free, they're open source. You then engage with the vendor behind, with Canonical, for enablement and for custom service agreements. Will get you to market fast. Updates and security are critical in the consideration, and if you are running in production, it's really something that should be kept front and center when doing your consideration. So overall, if I were to summarize, Ubuntu Core is an enterprise-grade solution. It is ready for production, and if that's your use case, then and you don't have an expert in-house team of dedicated kernel engineers committed to the ongoing maintenance and security and updates of your solution, then Ubuntu Core is probably a more feasible solution. All right, I covered a lot today. Hopefully, I provided enough value, but I do want to open the floor for questions.
All right. So again, I hope that you all enjoyed the webinar. And for this part of the section, I'm joined by Diego, one of the IoT field engineers at Canonical, and he will help me to answer some of the questions. So I'm taking a look, trying to group them into the same category. There's a question regarding the control of updates deployed on the fleet of devices, and in particular, this person is asking whether it's possible to check if the updates will lead to issues in a lab before deploying on the fleet of devices. Diego, do you want to take this one?
Yeah, sure. So this is what we usually recommend. So actually, Ubuntu Core is maintained, is delivered, and it's maintained by Canonical. And also we take care about the operating system itself, that's Snap-based, in terms of the kernel Snap, Snapd, that's responsible for managing the snaps running on the systems, and a lot of others, system Snap, like Modem Manager and so on. And the main advantage is that you can refresh the canonical snap automatically on your device. But also sometimes this is not the most convenient way to do that in production. This is just because there are many interactions between different snaps, especially when it comes to customer snaps. And what we recommend to our customers is to test in the lab the version, or better say revisions of snaps that makes your system running. And then whenever your system test passed, you can deliver on the field. And you can do it in different ways. The first way is called refresh control. And with refresh control, you can actually specify exactly which snaps are allowed to run on your system and at which revision. Uh, this is a feature that is available today, and it is called gating snaps. But we're also developing a more powerful version of gating snap that is called validation sets, and this is now in beta version and will be available for production in Ubuntu Core 22. And another way to do that is to using progressive updates. So it's a kind of canary updates. It's also called canary updates. So you actually select a subset of your devices. This is automatically performed, and a given percentage of devices will receive the update. And so you can test your new snap revisions on a subset of the devices, and whenever you are sure enough that your code works properly, you can refresh all the devices or roll back the small percentage of devices to the old revision.
Fantastic. There are some questions around snaps, and we did cover it during the webinar, but maybe a quick one is whether also the kernel and the drivers, are they also snaps in Ubuntu Core?
Yes, actually, every single piece of software that runs on a Ubuntu Core device is a snap. And in particular, the kernel snap contains all the kernel tree, including driver and BSP as well.
I guess a follow-up maybe to this one is regarding the device tree to define the hardware on the board. Is that a snap too? If so, how does it work?
So this is part of the kernel snap. And in the past, it was not like this. It was in the gadget snap. So the gadget snap is a specific snap that contains the bootloader and board specifics, like the file system layout or system configuration in terms of snapd system configuration. And we moved recently means 6 months ago, more or less, the possibility to have a link between the gadget snap that actually consume the DTB files into the kernel snap. So actually, so far, for the ARM architecture, we have the DTB contained into the kernel snap.
And one question that is often raised, and I see it phrased in a couple of different ways here, is regarding custom BSPs. So how do we get custom hardware support with Ubuntu Core? Is that something that we offer at all to our users?
Yeah. So we are always developing our support to new hardware and new boards, depending on customer demand. And we also provide specific professional services that call enablement, that consist of the porting of Ubuntu Core on an unsupported hardware. In that case, we take care to modify and maintain the Ubuntu Core on the specific board in terms of the system snaps. So the kernel snap, the gadget snap, and eventually snapd if this is impacted. Another thing we do also is certification. So we can certify devices. It's kind of a canonical stamp that we provide to the customer interested. And in that case, the device certified is also tested by a specific certification suite that we tested on our IoT device lab.
I guess related to the snaps discussion, there are a couple of questions on the Snap Store. Maybe we can combine them. So one question is asking whether there will be any guarantees of maintaining the Snap Store itself, but also whether it is possible to install all the snaps available in the Snap Store on Ubuntu Core. So considerations around installing snaps and the maintenance of the store itself in the decades to come.
Yeah, so, well, there are, from a technical perspective, there is a single store, but actually, from a customer perspective, there are very different stores. The one is the global store. It's a free store in terms of any developer can publish their software on. And each publish, once the snap is published, it should be reviewed. And if passed the review, it will be published, and anyone can install that snap. There is also the idea of a brand store. Brand store is a private store. So a customer take advantage of the brand store to publish their own IPs, their own snaps, and to keep up to date the device on their fleet. The store is responsible for refreshing the snap, so keep the snap up to date. So Canonical is continuously developing a new feature on the store, and it plans to support for decades the store. In case the store is not available, the device they are 100% functional. So the store is not needed for the device to be functional. The store is actually needed to keep the devices up to date. Okay. Eduardo, do you have any further questions? I don't know if Eduardo is still online. So let me see if I can grab other questions. Sure, I can get the list. Yeah, it looks like Eduardo have some problems. So let's have a look on other questions. So which debugging tools are available on Ubuntu Core compared to Yocto? So well, let me say that all the standard Linux debugging facility, talking about GDB, hardware emulation, and so on, can be still using Ubuntu Core. Additionally to this, there's a number of debugging facilities specific to snaps. To name a few, the Snappy Debug Snap, that it's useful for debugging full confined snaps. So it helps to identify the right interfaces and changes to make the snap work within its sandbox. Snap Try, that speed up development, allowing the developer to make live changes on the snap, avoiding to uninstall and reinstall the snap once this has been modified. Snap Run, that can be used with the strace and GDB options as well, so it can be connected to a GDB and can produce strace output. And of course, the journal CTL, system CTL, is a powerful source of information whenever debugging snap, especially when we are finding the right interface to add to the snap. And of course, also, another one, the last one, is a Snapcraft debug. Whenever you build a snap, the Snapcraft debug automatically opens a shell within the snap virtual environment. So if a build error occurs, with SnapGuard debugger, you are able to see the environment and look for the error. Oh, I see Eduardo is back.
Thank you, Diego. Yes. Yeah, I had a problem with my internet connection. Thank you for taking those questions. I can continue with a few more questions. So there's one I can take regarding the possibility of upgrading a device from Ubuntu Core 18 to 20. And it's currently it is not possible because the disk layout is different between the two versions of Ubuntu Core. But we are working hard on making the possibility of upgrading from Ubuntu Core 20 to Ubuntu Core 2022, the new release that is coming this year. Let's see the remaining questions. And Diego, you covered the one on the security vulnerabilities in Ubuntu Core, or while my connection dropped, or?
No, actually, I didn't cover that, but I can cover now.
Right. So if you have a minute, there's a question regarding how are security vulnerabilities managed in Ubuntu Core.
Yes. So the management of vulnerability is performed for Ubuntu Classic, that means desktop and server, and as well for the Ubuntu Core by a specific security team. That security team is responsible for several tasks. Auditing, so it search for vulnerabilities on Ubuntu packages before they are officially supported, and tracking. So the security team look into the Mitre CV database for vulnerabilities, triage, and add into the Ubuntu CV tracker. Fixing, and the security team provide a fix for the vulnerability. And testing, of course, so it will perform the test and all the regression tests on the affected package, and then finally the delivery. So we have a site that's called Ubuntu Security Notice, with actually list all the CVE fixes and the packages that have been impacted.
Awesome. I can combine two more questions regarding snaps. One is on the application isolation in snaps. So we have the standard Linux security capabilities like AppArmor, cgroups, and seccomps to confine applications. And someone is asking regarding negative aspects of using snaps. I would say that in case developers lack the necessary experience, it may be recommended to have some training, some workshop before deploying snaps. Also, there is no clustering support, and the network functions need to run on the host network interfaces. Let's see, one more questions. One final one is regarding build root. So a user is asking the role of a build root in building embedded Linux distributions and whether it differs with Yocto. And build root enables you to build these embedded Linux systems through cross compilation. The output is a root file system image. And I would say the main difference with respect to the experience of building with Yocto is in the simplicity that Buildroot tries to give the user. So the core logic is implemented in a make files that have a very limited, relatively speaking, limited number of lines of code when compared to the recipes and layers and all the bit-bake information stored in Yocto. So it differs a lot in terms of complexity with the Yocto project experience. All the configuration information is in one file, and also Buildroot tries to reuse to the extent possible well-known tools like kconfig to specify the architecture, the kernel, the bootloader, etc. And then special cases, they are handled in extensions in Buildroot. I believe we more or less covered most of the questions. Diego, do you see anyone that we are missing at this stage? Otherwise, I believe we've been running for more than 1 hour.
Yeah, I think yeah, we are running a bit over. So there's a lot of interesting questions. It's a pity that we don't have enough time to answer to all of this.
Yeah, and please do get in touch and send us an email in case there's something else that you would like us to cover or to provide any feedback. It's always very welcome. So I guess that's all from our side, and thank you very much for attending this webinar.
Thank you.
Thank you. Bye.